Okay, so last time we were talking about networking and remote procedure calls. I gave a very quick introduction to what networks were. I glossed over some material because I wanted to get to RMIs quickly, given that that is main subject matter of Lab 3. So I'm going to go back and revisit last week's lecture and go over some of the material that I skipped over in the interest of time, and we'll do that now. Okay, so keep in mind we talked about what is a network, define what is a distributed system first, and then we said what is a network, talked about local area networks, wide area networks, we introduced a network protocol stack, TCP, IP, and so on. Okay. What I had not talked about last time was network topologies, difficult topologies that are in use when you design a network of some sort, and I talked a little bit about that. Okay, and then I'm going to revisit some of the material on RPCs and RMIs, and then we will switch to the actual subject matter for today's class, which is going to be network and distributed file system. Okay? So continuing from where we were last time, I talked about LAN and WAN, local area networks and wide area networks, and typically depending on how nodes in a network are connected, you get different topologies. Okay? And we'll talk about several of these. So the simplest one is what is called fully connected topology. Here there is a physical wire or a physical connection from every node in the network to every other node. Okay, so this is basically the structure you get is a clique. It's a fully connected graph. And if you have a network structure of this form, then as you can imagine, any node can directly send a message to any other node in a single hop. Okay, there is no need for any intermediary because nodes are fully connected. Okay. There are order of n square edges for n nodes, which makes it hard to build as you have more and more nodes in the network, okay? But it's very efficient from a communication standpoint. Failure of any node doesn't actually impact any other nodes because they can still communicate with the rest. Okay? Now clearly you can do this for some simple forms of LAN topologies, but for wide area that's a no-op. Okay? You cannot just have a wire, a physical wire going from every machine in the internet to every other machine. Okay? That just doesn't work. Okay. So most real topologies tend to be partially connected, not fully connected. Okay. So in partially connected topologies, you have physical links going from some nodes to some other node. Okay. So there is a path from any node to any other node, which allows you to actually send message from any machine to send a message to some other machine, but not directly. So you have to go through some other node. Okay. So that's what is referred to as a partially connected network topology. Much less expensive because you don't have as many links in the graph. You can, depending on how sparse the graph is, you can have order of n links if you want to make it a chain or some sort of a partially connected network. Okay, but less resilient to failures as well. You may have what are called network partitions. So some nodes can get disconnected from the rest of the network. Okay, so if you follow the, let's say that edge fails, okay, you have two graphs. Okay, nodes in one subgraph cannot send a message to another subgraph, nodes in the other subgraph because the network has got partition. Okay. This often happens when, let's say you have an ISP and your main internet link goes down. Okay, your LAN network gets disconnected from the rest of the world. So you have basically what is called a network partition. Okay. So failures can partition the network. Point-to-point topology is not as robust to handling failures. And sending messages requires you to go through multiple hops. Okay, so in this case, if this node wants to send a message to that node, you will have to go through some intermediate hops, okay, through some routers. Okay, you can communicate, but you will have to basically, messages will have to traverse multiple hops. As is mentioned here, typically, if you have a WAN, you will have a partially connected network, okay, never a fully connected network because it's too expensive. So the next topology we'll talk about is a tree structure. As the name suggests here, there is a root and then there are descendants in the tree structure. Okay, there aren't links going from one subtree to another. So it's a tree, not arbitrary graph. Okay, so Communication here basically says if node A wants to communicate with node B, a message has to go up the tree to the first common ancestor and then it has to traverse down the tree. Okay, that's how communication will actually take place. Okay. Corporate networks typically like hierarchies. Corporations like hierarchies. Okay. So even in networks they have hierarchies. Their domain names have hierarchies. So network structures also have hierarchies. In many cases, you may have a headquarters sitting at the top of the tree, and then you may have leaves depending on where your geographical or branch offices are. You may have a structure of that. Not necessary, but in many cases, you may have either a logical hierarchy of a tree or a physical tree. Okay? And because a tree is also a partially connected graph, it is also not very robust to failures. Any link failure in this tree is going to essentially partition the link. Okay? Depending on where that link is, you may have different nodes and different subgraphs. Last topology for point-to-point is what is referred to as a star topology. Okay? So in the star topology, there is a node in the middle, okay? And all other nodes are connected to that node. Okay? So any node can send a message to any other node in this topology in 2 hops. Okay? At most 2 hops where you send the message to the middle node and then it forwards it to the node that you are sending it. Okay? This form of this topology is very common when you have things like a Wi-Fi network. If you have a home wireless router, it is essentially your router is the node in the middle. All your clients are 1 hop away from the router. Okay, so if you want to talk, if you are on that LAN and you want to basically talk to a printer, let's say, you will send a message. All your messages will flow through the router from your machine to the printer. Okay, 2 hops. Okay, there are many other networks that also use star, but Wi-Fi networks are especially common. A single access point Wi-Fi network, not corporate Wi-Fi networks which may have many access points. Okay. Now again, this is partially connected, so if the node in the middle fails, if your router goes down, the network is down. Okay. Same is true here. The node in the middle, the central node, is the most important node in this network. It is a node that enables all of the communication. Okay. So if it is going to fail, then your network as a whole will be down. Okay, not very robust to failures. One more I forgot. So those are point-to-point topologies, and now we look at some ring topologies. Now you don't see very many ring networks anymore, okay, not physical rings at least. You do see logical rings that are often used in peer-to-peer networks. Many P2P networks are organized in form of logical rings, not physical rings. But once upon a time, ring topologies were actually not only very popular, but also very common. Ring topologies were competing with Ethernet networks. Okay, Ethernet and rings were the 2 forms of LAN. If you actually went to buy a PC, you had to specify what kind of card you wanted, an Ethernet card or a token bus card, and a token bus was essentially a ring network. Okay, so you had these 2 competing form of LAN, they didn't interoperate. And then you know which one won out, because you don't hear of these token rings anymore. So Ethernet just took over, token rings faded away. But yes, so you don't actually construct LANs, physical local area networks in this fashion. Nevertheless, interesting to study. So here, as the name suggests, all the machines in the network are organized in the form of a ring. Okay? And basically, any node can communicate with any other node by just sending a message to its neighbor, which forwarded to its neighbor, and so on, and the message traverses the ring until it reaches the destination. Okay. So, given n nodes, you may have a message may require at most n-1 hops. If you have a unidirectional ring. Unidirectional ring says messages can either flow clockwise or anti-clockwise. Okay. So you have to pick one and that's how the messages will travel. So in this case, you may have, on an average, you will have n/2 hops. But in the worst case, you will have n-1 hops for n nodes. Okay. If you have a bidirectional ring, which means messages can flow in either direction, you can pick the shorter of the 2 paths and send it along. Okay. So you can decide, depending on which node you want to send, is sending it clockwise going to get it there faster or anti-clockwise, and you pick one of them. Okay. In this case, the message has to go at most n/2 hops. Okay. Because you don't have to, you can pick the shorter of them. Okay. Both of these will have problems if any node in this network actually dies. Okay. So basically you will have a network, your ring will get partitioned. Now keep in mind that in token bus networks, your machines that were sitting on the networks are also responsible for forwarding. Your machine is part of the LAN. Okay, so all other messages that are flowing through this LAN actually go through your machine. Okay, so your machine is part of the forwarding part of the network. There's a forwarding function in the network. So if your PC dies, your token ring actually will get disconnected. Okay, so you need to address that in some way. Okay, so here is and as I was mentioning, peer-to-peer networks of many forms, they actually use logical ring topology. They are actually built to be robust to nodes coming and going. Because in a P2P network, you can actually disconnect your P2P client, and then your client can't do any forwarding anymore if it is responsible for forwarding. So you need robustness in ring networks to ensure that the network LAN continues to function. Okay, one way to ensure this is to have what are called doubly connected ring. In a doubly connected ring, each node can not only talk to its two immediate neighbors, can also talk to your neighbor's neighbors. Okay. So now if this node goes down, okay, you can just hop over this node by using that link. Okay, your network ring is not going to get partitioned. Okay, so in a doubly connected network, you can handle some failures. Okay, if two adjacent neighbors both go down at the same time, your network will get partitioned. But on an average, if random nodes fail, then you can still tolerate those links failures by just hopping over those links and just sending a message directly to your neighbor's neighbor because your neighbor is down. Okay, so that's one advantage of a doubly connected ring, which is it is more tolerant for failure. Okay? Another advantage is that you can send the message much faster. Okay, because the inner ring basically allows you to skip nodes. Okay, so if you have to go, if the actual node you want to talk to is 10 hops away, you can just skip nodes by just sending it on the fast path. You can just go that way, and then you can go to the right node. Okay, so here messages take at most n by 4 hops. Okay, I'm assuming it's bidirectional. Because you can skip nodes, you don't have to go through every node. Okay, you can just skip in order to get there faster. Okay, any questions on doubly connected ring? Okay, so the last topology we'll talk about are bus-based networks. These are the ones that we normally see. Ethernet is an example of a bus-based network. Okay, the bus-based network, as the name suggests, there's a shared communication medium, the bus, which in this case is the network itself. And all nodes actually sit on this bus. So here is an example of a linear bus. Okay. They share the connection. Okay. So what this also says is that at most one node can actually send a message to any other node at any time. Okay. If two nodes try to send a packet at the same time, that packet is going to collide. Okay. They will basically, the message will get garbled. Okay. So you need a way by which only one node can communicate. Okay. And then once that node is done, some other node gets it done. Okay. So in bus-based network, you need a form of arbitration. Just as in the system bus, you need the system bus, it has to arbitrate. If the I/O device wants to do DMA to memory, the CPU also wants to access memory at the same time. You cannot have all of these things happen simultaneously. Okay, each one needs to go in turn. Same is true here. If two nodes want to send network packets at the same time, one node has to back off, and another node has to go first. So it's much cheaper to build these networks because it's shared. But the networking becomes a little more complicated because simultaneous transmissions are not allowed. I shouldn't say they're not allowed. Simultaneous transmissions cause problems. Okay, they cause collisions on the network and your messages get garbled. Okay, so as I said, Ethernet LAN uses this structure. Okay. And I should also mention that this is true for early forms of Ethernet. Okay, now as you go to gigabit and 10 gigabit Ethernet, you have switched networks, which basically means that not every packet goes to every node anymore. Your switch can start doing smart things and not forward packets to all the nodes needlessly. But You can still get Ethernet switches that essentially do this. Whenever a node sends a packet, it goes to all the other nodes. It broadcasts, the node that is destination receives it. The other form of bus topology is what is called a ring bus. Okay, so here you basically have essentially a ring which is the shared medium, and nodes are tapping onto the ring. The same is true as a linear bus, except that you can assume that there's a loop that goes from one end to another and you get a ring bus. Okay, so same, all of what I said here is going to apply to the ring bus as well. Okay? Only one node can communicate, there can be collisions, and so on. Okay, there needs to be some arbitration. That's it. Any questions on this? Okay, so whatever I said here is true whether you actually have a physical wire connecting nodes or whether you are doing this on wireless. In wireless, your medium is air, but that doesn't change anything that I said here. If you have a Wi-Fi network, okay, and basically you can have only one node send on one channel at a given time. If two nodes try to send packets on the channel, they will collide. Okay, channel is a frequency over which you communicate. Okay, different channels are independent, so you can have independent communication, but on any given channel, it looks exactly like Ethernet. Basically, it's shared. And you don't have physical wires, you just have an access point that you're talking to. Okay, so packets can collide over the air, so you need to arbitrate. Okay, only one node can talk to the access point at any given time. Okay. So that's what I had to say about networking material that I skipped last time. I'm going to go back quickly and talk a little bit more about client server and remote procedure call. I did that quickly and we were running out of time, so I want to emphasize that again. Okay. So as I mentioned, client server model is a very popular model for designing distributed application. Okay. So in this model, your application functionality is split into two parts, a server part and the client part. Okay. The server part of your application provides a service, the client part makes requests of the service. A very popular model for building variety of different applications. Print servers are an example of where you have clients printing for print server, or network server is an example of this. Distributed file servers are an example of this. Email is an example of this. Typically emails arrives at a server, you have a mail client, maybe a laptop, maybe a phone, you access your mail on the mail server through that client. Right? Very popular way of designing distributed applications. As I mentioned, the other technique that is typically used in some cases is the peer-to-peer model. Okay, in a peer-to-peer model, there is no distinction between nodes. In a client-server model, there are nodes that are either clients or servers. Okay? Servers are more distinguished nodes, they are the ones providing the service, and clients are simply accessing the service. In a P2P model, typically a node provides both functions. It can be a server or a client, which is why it's just called a peer. And we won't talk about P2P anymore, just wanted to mention that. Okay, so server is a process that provides a service, client is a program that uses the service. Typically, clients and servers run on different machines. The standard assumption is there are many more clients than servers, typically. Okay, so small number of servers, large number of clients. Okay. Many ways to write applications using the client-server model. The one that I mentioned last time was using RPCs, remote procedure calls. So RPCs were designed, or not designed, were made available commercially first by Sun Microsystems, which designed Solaris, a form of Unix that's still in use today. Yeah, so this was, I think, 25, 30 years ago. Yeah, it's a very popular way of writing applications. The advantage of using RPCs is that you use your same abstractions that you are used to. You take your application, you partition it into methods or functions, and one method calls another method. Right? In RPCs, it just so happens that some methods are remote. They sit on another. The code for those methods sits on another machine. Okay? And the RPC subsystem, in this case, takes care of all of the networking for you. So you don't have to, you as in the programmer, don't have to write code to actually make a request to a method sitting on another machine. It's all taken care of for you. Okay. So what happens is you typically write the interface to the method, and then you run this program to a special compiler in RPC compiler. The RPC compiler generates what is called stub code. The stub code has all of the details of how do you actually construct a packet, how do you send that packet or a message to the server, how do you get back the response, how do you hand that response back to the user process that called it, and so on. So this is the code that you are actually going to link to your application when you compile your application. Okay, so you write some C code. Okay, this is typically done in C or C++. Same concept applied to Java, but let me just tell you what happens in C. So you will write the high-level C code, which is going to either implement the server method or call this code that calls the server method, and then you run it through a compiler, typically an RPC compiler like RPC gen, and it will generate a file for you. Okay, that file will have all of this code. And you take that code and your code and you link it together and you construct one binary. Okay. Then when you run the binary, when you make the RPC call, your call will internally go to the stub code and it will do all of these things for you. It will build a message. Okay. But first you have to, not build, first you have to bind to the server. You have to first find out where the server is running, okay, and establish a connection to the server. And typically or TCP or UDP, okay, depending on whichever protocol you have configured in the RPC compiler. Or specified to the RPC compiler. So then once you bind to the server, you build a message, you will then construct the message, you will send the message over the network, you will wait for a response. Okay. And then when the response comes back, you will unpack the reply and you will return the message. Okay. On the server side, you are going to basically just automatic code generation will do all of these tasks for you. Okay. So you will sit in a loop waiting for requests to arrive over a network. Okay. The clients will send those requests. Whenever each request comes in, you will unpack whatever is in the message. You will figure out what method is being called. Okay, you may have more than one method on each server. And then you will figure out what procedure is being called. You will invoke that procedure with the right arguments which are also sent with that message. And then you will take the results and send it back. In addition to all of this threading is also taken care of for you. Okay, typically, most RPC compilers will automatically generate code so that every request that comes in can spawn off its own thread. Okay, so it's called a thread per request model. A request comes in, new thread is started up, and then it's given that request. It goes off, it processes your request, sends back a reply, and then the thread is terminated. Okay, so every request can start a new thread. Okay, you can also have a static pool of thread depending on how sophisticated your RPC compiler is. Okay. So some of these concepts will apply also to Java and specifically to the lab. Okay. So we should keep that in mind, although this is all done in C, the same kind of concepts apply. Okay. Very quickly, I'll recap what we had talked about as far as RMI is concerned. Okay. Remote methods or remote method invocation is are RPCs in the Java world. Okay. They are built into the language. Okay. So it's sort of part of the language. RPCs are not part of C. The libraries that are written on top of C. Okay. In case of Java, RMI is built into the support for RMI is built into the language. It is part of the Java spec. Typically, what you have to do is you need to provide some objects or classes that will allow you to figure out where is the server, bind to that server. Okay. This is done through a bind method. You can, and the way you figure out where is the server is through a lookup method. Okay. So you ask some directory service saying, where is the server that provides this service, and you name the service, or the method you want to call. And the server has to have registered with that directory service. And it will basically tell you that the server is running on this machine, this is the IP address, this is the port. And then your client stuff will actually use that information and bind to that server. You don't actually go and write any code to set up connections. The RPC, the RMI object will do it for you. Okay? This is basically the object that is going to do all of the hard work. It's called remote unicast object. That's a class in Java. Okay, so this is the RMI registry. This is the server side name server. You have many tools. This is one that is called the RMI compiler, but there are many others. Okay, that's the one that will generate the stub code. Okay. So typically, so that's the background. So this is how you write RMI server and a client in Java. So to write the server, you have to do three things. You have to first define an interface, and those are the methods or the signatures of the methods that the server provides. That's the service. Those are the remote methods that can be moved. So that's the interface. Then there's an implementation of the interface. That's actually the code for every remote method. Okay. And the third is the main program. Okay. That's the program that's going to register the server with the name server, okay, or the directory service. Okay. So typically, to write the server side, you have to do those three things. So to the client part is much simpler. To do the client part, you have to first look up the server. Once you've figured out where the server is running, you just use the normal call syntax to actually call remote methods. Okay. You need to be able to handle a special type of exception called remote exception. Okay. Because if you make any mistakes, the server is going to throw a remote exception. This exception will come to you over a network, okay, rather than a local Java exception. Okay. So if you do those three things, then you have a client that will talk to your server. Okay. So let me show you examples of the three things on the server. So this is the interface part of the server. Okay. This is where you define what methods, remote methods the server is going to implement. Okay. This is what is used to actually generate the stuff. So here is a server that implements exactly one remote method. This is a hello world server. So all that it does is it gives you a string called hello world. Okay. So this you basically have a method that says say hello. Okay. That's this interface of your service. Okay. And as you can see, there is you have to basically extend this class called Java RMI, Java RMI. Okay, so that was the interface. This is the implementation of the server. Okay, so this is where you implement that method that you declared was a remote method. So basically, it's a trivial method to return a string. Okay, but this is where you will do all the hard work. In your lab 3, that's where you will actually put the server side code. So that's all it's doing. You've implemented a class, and this class is going to extend this unicast remote object class. And then this is the implementation of the method in that class. Okay, so that's the second part of the server. The third part, as I said, is the main program itself. Okay, so all you have to do here is to essentially create a new instance of that object. That's the load object. And then you basically register yourself in the server. So I'm a service, and this is the object that I'm exporting. And then you're done as far as the server is concerned. Okay, you don't have to set up connection. None of that code has to be written. Okay, all that is taken care of for you. The client side is also straightforward. Okay, all you have to do is first you have to look up the server. Say, where is this server running? Okay. And once you have done that, you just call the remote object. So you just say object.say hello. Okay. That looks like you are calling a method on a local object. It just so happens that this object is actually sitting on another machine. So your code looks exactly the same as if you are calling local object. Okay, so you can write it without too many new abstractions. Okay. And then you will basically, as I said, you have to handle something called remote exceptions. Okay, because if there's a network error, you will get an exception. Okay. This is a very simple client-server application just to illustrate the broad principle of how you are going to do RPCs or RMs. And this is a distributed application. The client is an independent process that's going to run on one machine. Server is an independent process that runs on another machine, and the two communicate over a network. It doesn't matter whether your network is a LAN or a WAN. The same code will work. Same code will work whether you run both the client and the server on the same machine, okay, but separate processes, or different machines. Okay, any questions on this before I move on to distributed? I wanted to re-emphasize this just so that the basic concept is clear for those of you at least who don't have a networking background. So we just finished the RPCs and RMI topic, and we are going to switch gears and start the next topic here, which is network file systems and distributed file systems. Okay, so we'll assume now, we are going to keep building. This is a 3-lecture sequence, but each lecture is actually building, each component is building on the previous one. So we did networks, what are networks, how do they work, and we said, how do you write client-server applications on those networks using RPCs specifically. Okay. Now we are going to look at a particular applications that is typically used or written using RPCs, namely distributed file system. Okay, very complicated application, but provides a lot of interesting convenience from a user perspective. Okay. The most common example of a distributed system, or the earliest ones. There are lots of them. Okay. So what does a distributed file system? Essentially, it allows you to access files stored on another machine. Okay. So typically, if you have a local disk on your machine, you can access those files. Okay. Now, what if you wanted to access files on another machine? Okay. If you have a distributed file system, it allows you to access remote files as if they were local files. You don't have to do anything different except form a connection to the server. And then the server will allow you to access those files as if they are local files. Okay. So given a set of disks attached to different nodes, you can share those disks between nodes as if they were all locally attached. Okay. So this is a form of resource share. Okay, you will see many examples of this. Okay. You probably have gone to the Ed Lab at some point or the other, or at least used it remotely. And what you see is if you log on to a Ed Lab workstation, your files that you are actually accessing are not local to that machine. They are actually stored on a server somewhere else. And you are using a distributed file system. In that case, it's NFS, network file system, to access those files. And there are many other forms of distributed file system. In Windows, you have network shares. In Macs, you have Apple file partitions. And so I'll show you examples of that. Okay, so there are many issues you have to deal with when you talk about designing a distributed file system. Okay? And these are some issues we have also seen before when we talked about distributed systems design in general. Okay? First one is naming and transparency. How do you actually name files that are stored on another machine? Okay? We'll see examples in just a moment. Okay? What is the form of remote access? We'll see that there are two principal ways of designing a distributed file system. Okay? What is called a remote access model or a caching oriented model. Okay? And we'll see what are the differences of these two forms. Okay. You can use performance optimizations in the form of caching, but we'll see that that makes some other aspects more complicated. Okay. And we'll see what those are. We'll see that you can make the server stateful or stateless, and you'll also see that you can employ replication of your files to make performance better. Okay. So we'll go through each of this one by one. Okay. So let's talk about the first one. Okay, that is naming and transparency. Okay. So here issues are how are files named, do file names reveal their locations, and do file names change if the location moves or the user moves. Okay. There are two key concepts here. One is called location transparency, the other one is called location independent. Okay, they sound similar, but they're actually slightly different things. Location transparency says that the file name does not reveal its location in terms of what server it is stored on. Location independence says that the file name doesn't even change if it moves location. If it moves from one server to another, the file name remains the same. That's a handle that is not going to change. It's not bound to the machine. It's bound to the object of the file. Okay, and let's look at some examples. Okay, so the last point here, it says most file systems actually do provide location transparency, but location independence, many of them don't. Okay, very few do. Okay, so let me give you an example. So I am going to connect to a server here. Okay, I'm going to use the Apple file protocol. It's a form of a network protocol. That's a server. Okay, so can you see?
That way,
I can make it bigger. Okay, so I just have a name of a protocol and a file server. We'll see what happens in just a minute. So we connect. now I have a network share mounted on this local machine. Okay, you can look at it graphically or you can look at it here. Okay, so let's look at what it looks like here. So that's basically the network share. So here is the name of the server, and that is basically the volume that I mounted on the server. That's the user, and that's where it's mounted. So if I actually go in, so I can just now so these are all files that are not local, they are actually remote. Okay? But I'm accessing them as if they are local. Okay? Every request I make now actually has to be sent off to a server. The server is sending, so even if I do ls, which is the list files in this directory, okay, that becomes a remote procedure call, because it's implemented using RPCs. The RPC call goes to the server implements that request or executes that request, sends back the response. Okay? So distributed file systems are typically implemented using RPC. Okay? So two things. Okay, first is accessing remote files is now just as convenient as accessing local files. Okay, you can do the same thing graphically. Here is that volume I just mounted, and then you can go into public HTML or whatever, some directory. Okay. So these are all remote files. Okay, you can access them, you can do whatever you need to do. Okay. So now let's look at file names here. So here is so typically the name is, so that's the mount point. It says /volume some mount point, and you can access a file. That does not necessarily include the name of the server. Okay, that's basically tied here. When I did this df, you could see that server name was here, lambda.cs.emacs.et. Okay. But when you access a file, you can leave out the server name. Okay. That basically gives you a form of location transparency. Okay. Compare that to URLs. If you have a URL, which is another form of naming, so naming for the web, basically you have to do things like this. Say registrars calendar. Okay, go to the academic calendar. So this URL actually has the name of the server embedded in it. This is not location transparent, because you have to specify the name of the server as part of the name of the object in this web page you are trying to retrieve. Okay. If you have the name of this form, this name does not have the server name embedded in it. Okay. The server name is known to the OS. Okay. The OS knows when you say volumes to what server actually has this file, but you don't have to actually say something like // server name /volume. So this is another form of naming. Okay. You can actually, in Windows you can do // and give this name. You can actually specify this machine. Okay. In that case, that name is not location transparent, because the location or the server name is embedded in the file name. Yeah, but if you leave that out, in this case, the name is location transparent. Okay? So different conventions are in use depending on what file system and what operating system you're talking about. Yes.
So we cannot have the files with the same name on different disks connected to one node.
Can you have files with two different names?
With the same name.
With the same name. You can have files with the same name because they may have what are called different mount points. Okay, so simplest way to say this is, if you know Windows, you can have a C drive and a D drive. You can have the same file called foo.txt on different drives. Okay? Same thing is true here. I could mount another volume and it would have to have a different mount point. Okay, so volume bar, you can have something like this. Okay, so you can have the same file because they have different prefixes, it's okay. Any other questions here?
How is that independent then?
How is this not location independent? Location independent says that if I move this from one server to another, you can still access it with this name. That is not true, right? Because the name will change. Yes.
But isn't it though? Like when you,
This part of the name hasn't changed. The file
Right.
name, but the full path name, there is some part of it would have changed. That's
Okay.
what we mean by location independence. Okay, if you actually do your cloud term paper, okay, you want to know what location independence means, you go and look at this service called S3, Simple Storage Service. Okay. The Simple Storage Service, you have each file is given what's called a handle. Okay. It's a large integer of some sort. Okay. That integer, you don't actually know where the file is stored. Okay. You just present that handle to the system gives you back the file. The file can move, in fact it does move from time to time, but you can always go back to it with the handle. Because they move it internally, they move it for load balancing reasons or other reasons, so the name doesn't change. In this case, you say the storage space disk filled up, I want to move this entire directory to some other machine, you can no longer access it with that. The name, some part of the name has to change. Okay, so that is what is called location independence. And many file systems won't provide that, they will only provide location transparency. Okay, so that's this relative names and absolute names. So what I was showing here, which is often used in Windows, is what is called an absolute name. URLs are also absolute name. Because you have a server, name of the server, and a path name on that server given to you. That's called an absolute name. Same thing is done in Windows, where you have / name of the server, some share or network share on that folder, and a path name on that share. Okay, so if you have machine names and path name, then you have what are called absolute names. The advantage of an absolute name is you specify all of the information needed to access it. You have the name of the machine, the directory on the machine, and the name of the file. Okay. It is scales easily because there's not much work that the OS needs to know in order to figure out where that is. Okay. All of the information is specified. Okay. Disadvantage is the user actually has to specify much more information. Typically, the shell will take care of that for you, but something has to specify it to the OS. Okay, so there's more awareness on part of the user. It's file dependent, cannot move, somewhat harder to share, and if it's not location transparent, it makes it not fault tolerant either. Okay. So as opposed to Windows NT and Apple file system, there's another file system called NFS, widely used in the Unix world, that has a slightly different philosophy. Okay. So what happens in NFS is when the system boots up, okay, you specify a table, okay, to a set of configuration parameters to the OS. It says, here are all the servers I want to access, and take those volumes that those servers are providing to me and make them available at this point in my local file system tree. Yes, so I don't know, there's a picture here. I put the picture in the. So, let me just draw another picture, simpler. This is more complicated. Okay, so let's say you have a local machine where you have slash home, or let's call it users. Local. So this is your local file system area. Let's assume that there is a file server. That exports a part of its file system namespace to some other machine. Okay, when this machine boots up, it has to specify a configuration file which says take this file server and then take these directories, okay, and make them available at this point in the names. So when you actually do cd/users, okay, you are actually accessing remote files at that moment. Okay, you are accessing those files with a local name, but then you don't actually tell You cannot tell just by looking at the name that these are remote files. You are accessing them exactly the same. But this mapping is done at boot time. Once you do this mapping, you don't no longer have to specify the server name in the path. Okay, that's automatically taken care of for you. Okay, let me show you an example to make this a little more explicit. It requires us to go into go to the same server that we used for the previous example. I'll show you some. So lots of volumes here, but the last 4 volumes are NFS volumes. Okay? So these volumes, this is basically specified, this information is specified at boot time. It says take this server, that's the name of the machine, that's the path name of that server. So that's the network volume that the server has made available, and make it available at this point in my local file system tree. Okay, so if I actually cd into this directory, okay, I'm actually looking at files stored on this machine. Okay, but just looking at this, I don't even know the name of the server. This could be any arbitrary point in my local tree. I could have said /foo in this case, and if I cd /foo, I would actually be here in this directory. Okay, so you can see that there are many volumes here. So if I actually do exactly what I said, so you can do RPM. So these are Linux packages. All these files are remote, okay? But if I look at what directory I am in, that directory name doesn't reveal anything. It just looks like some local files, local directory, except that all these are coming from another machine. Because there's a mount point and you mount it. Okay? And the way this has got this mapping was established is you have to specify it into a table, as I was saying. Here is the table. So you'll see that this is the line that specifies that mapping. It says go, this machine has this volume, okay, this directory, take that and mount it here. Okay, so this is the local part of the subtree where that is going to be available. Okay. So when your machine boots up, it will read this file, it will establish all of those partitions, and then you are done. Okay. Now this is referred to this network's this distributed file system, excuse me, is what is referred is what's called NFS, network file system. Okay. Somewhat different from others. Okay. So it is location transparent. Okay. The mapping can change across reboots. I can go into that file I just showed you and mount these a different path. Because next time I boot, that same volume will be available somewhere else. Okay, so the path name can change depending on what the mount point is. Okay. Disadvantage is this unified strategy is hard to implement because the same remote file can have 2 different names on 2 different machines depending on what the mapping is. In one place you can mount it at one location, another machine you can mount it on another location. And this will make it much harder for users to figure out how to access a remote file. Okay. Same example here. So this is, I think, a mapping of what is done in the EdLab. So you have several servers, server 1, server 2, server 3. These are the volumes, these are the home directories. Okay? And these are typically mounted on a local machine, okay, as your home directory. So when you access your home directory on an EdLab machine, the files are actually remote. Okay? And this file establishes those mappings. So there's a directory for 377, which we no longer use. At one point we used that extensively, but that was actually a volume on some server. Okay, that's another example. Okay. So there are some other file systems that use a different naming strategy. In particular, there are some that use what is called a global namespace. What we mean by global namespace is independent of what machine you are accessing a file from, the file has the exact same namespace independent of where you access it. Okay, there are 2 examples of this. There is something called the Andrew file system, okay, which was developed at CMU, commercialized, available now in Linux, also available as commercial file system. There's another one called the Sprite file system. that made this naming convention popular. Okay. The simplest way to understand global name convention is to think of the naming convention in the web. The web also uses a globally unique name convention. Okay, so if you want to access the home page of CNN or New York Times, you basically have to specify the same URL. The URL doesn't change, okay, regardless of what machine you access it from. Okay, it's always www.cnn.com/index.html. Okay. The same thing is true also in this file system. So what you actually do in this, in the Andrew file system, basically there's a unique namespace. So there is /AFS. Every server, okay, basically attaches to this node. Okay, so let's say there is there are two servers, just to make an example, a cs.umass.edu server and a ec.umass.edu server. And here we have so any machine, if you have the permission, you can access any files on any machine anywhere in the world, okay, without doing anything special. All you have to do is just specify, just as you specify URL, the proper pathway. Okay, so you say /AFS. In this case, we will say ec.umass.edu. And if that directory is, well, in this case, world readable, if you just do this, okay, your machine will automatically establish a connection to that server, and it will make that directory available. And you will see that this looks very much like a URL. So files have the same name. So the name is basically always starts with a prefix which says this is the type of the file system, Andrew file system. You have a server in there, server name, then your directory of that server. Okay. No need to specify network shares, none of that. Okay. It automatically establishes a connection and you can access files. Okay. This is referred to as a global namespace. So no matter which node you are on, your file names remain the same. There's one single way to access a file, just as there's a single URL for every web page, and you access that web page using that name. The same is true here. There's a single name for a file. No matter what machine you are on and where you are, you can access that file. Okay. So basically, when the client starts up, it establishes a connection with the Andrew file server, and then basically gets the structure, and then you can access it in this fashion. Okay. So I already mentioned the naming is consistent, it's easy to keep consistent. Disadvantage is it's basically difficult to keep the file contents consistent during caching, because many nodes can access these files. You have to ensure that the files are consistent. I'll talk about consistency in just a moment. That's the next thing on the list. And then you have to ensure that if you have a global namespace, you are going to be able to scale. Okay, that's another problem. When you have a larger and larger system, ensuring scalability of your system gets harder and harder. Okay, so performance is a problem when you have a very large file system. So that's another issue to keep in mind. Okay. So now let's talk about remote file access and caching. So the way to understand this is there are two ways to access remote files. Okay, one is called the remote access model, and the other one, as I said, is the caching model. I can draw a picture here to illustrate. Okay, so this, let's say that's the there's a file server, there's a file called foo.txt that is accessible to this client. So you open, let's say foo.txt in an editor, and you start editing this file. So how does the distributed file system or a network file system take care of this? One way is what is called the remote access model, which means every read or write you do on this file, Okay? It's actually sent off to the file server and is performed on this copy of the file. So if you say read the next 1 kilobyte of this file, or next chunk of this file, you send that request and you get it. If you update the file and hit save in the editor, all of the updated contents are sent over here and you basically update the contents of that file. This is referred to as the remote service or the remote access model. And the other one is caching oriented. It basically says the first time you open this file, you are going to bring a copy here and store it, cache it locally. From that point on, all operations that are done by this process are actually done to this local copy. Okay? And if you make changes, you update this file, eventually the changes are going to be sent back to the server. Okay? They are going to be cached locally, they are going to be sent off to the server eventually. So why do the caching model? Okay, what are the advantages of a caching oriented model? Yes.
It's faster
It's faster. Why is it faster?
because you make one network call, so you only have to establish one connection. It caches everything locally, then you're just working off the other solution. So you have to do that.
Okay.
It's also fault tolerant, you don't have to have a network all the time.
Okay. So two things I mentioned. One is that it is faster. That you have to take that with a caveat, and I think the caveat. The assumption is that requesting something over a network is going to be slower than requesting something from local disk. Okay. Under that assumption, it is going to be faster to bring that file over and make all of the changes to local disk. Now, that assumption, I should say, is not always true. If the file is actually cached in memory at the server, sending a network message over a fast network actually happens to be faster than going to a slow local disk. Okay? Because networks have grown faster. You can have a gig, so sending a message or a gigabit Ethernet, and if that file is cached in memory there, you can get it faster than if you have to send it off to local disk, which may take 10 milliseconds. Sending a message can actually take less than that. But in most cases, the assumption is true, which is if you store it locally, that access is faster than remote access. But you have to always take this with a grain of salt. It's always how fast is your network and how fast is your disk. If the disk is slower than your network, then this, what we said, is not true. And there are cases where that is the case. But in most cases, this remote access is going to be slower than local access. Yes, with that caveat, it is definitely faster. And so the other thing that was mentioned is if you do this locally, if your network goes down, okay, your file is still available. Okay. Now this may seem like an odd thing to do. Why is the network down or so on? This actually happens all the time. If you take your mail with you, let's say you take your mail on your laptop and let's say you go off somewhere, you're disconnected from the network, your copy of your email may actually be cached on your machine. You can continue to access mail. And that's called disconnected mode. Many applications provide you disconnected mode. If you actually do Gmail, you may have heard of offline mode. If you're on Gmail in offline mode, a copy of all your Gmail messages are actually cached on your local disk. So even if you disconnect and not connected to the network, you still have a copy. And later on, there's a synchronization that goes back. So if you have cached copies, you can disconnect from the network, or you can tolerate real failures of the network and your data is still available. If you don't have that, then you have to be connected. Otherwise, there's no way to access your data. Okay. So that's the good part of caching. It's faster, you can tolerate failures and so forth. So there is a bad part as well, not a bad part, something that's more harder to deal with. What might that be?
Concurrency, like when you're taking the data to the local machine and you're writing, and when you're trying to write it back to the server, by then the data might have changed to the server.
Okay. So let's say now there are two clients that are both accessing this file, foo.txt. Okay. So if you use the caching model, you'll have a copy of that file on this machine and a copy of that file on the other machine. And if both of these clients happen to update the file, you may trample on each other. You send these writes over, and then this machine also updates it, and then you send that write over, and you may overwrite the previous one. Okay. In the remote access model, all writes are actually sent there. Okay. So You make a write or you update it, you send it there. You make another write, you send it, and when you read it, you are actually reading whatever was written last. So you always have an up-to-date version. Okay? So there are two issues. One is to keep files consistent, and the other is files may become stale. If one is reading and the other is writing, and I update this copy, okay, and this one still has old version now, this client is reading an old version. It doesn't have the changes that are made by this client. So you have stale cache copies stale in this case. In another case, you have consistency problem where you have what is called a write-write conflict. Okay, two machines updated the file at the same time. Okay, one has trampled over the changes made by the other. Okay, that's also a problem. So whenever you have caching, you might have multiple copies of the same object in multiple caches, and you have to deal with what is referred to as cache consistency. Okay. Major issue with any time you have caching is to ensure that cached copies are consistent. Okay, so that's essentially what's being said here. What happens when all modifications sent back? What if multiple clients cache the same file? So if you design a caching-oriented file system, you have to answer this question and have some satisfactory solution. Otherwise, the clients will see weird behavior. Yeah, so you may say, I just wrote that file there. Why is it that I cannot access it? Yeah, this happens all the time. If you are actually editing your file on one machine and compiling your file on another machine, or different build machine and a development machine, you save it here and then you run make here. Sometimes it takes a while for these changes to actually go to the server. So this server may have an old copy of the file. It may not even see those changes. And you get weird compilation problems. You say, I just made that change, I run the code, I don't see my change reflected on the code. So these kinds of weird things can happen. Okay. So let me talk a little. So there are many ways to deal with cache consistency. Next time, not today, we'll do a case study of NFS. We'll see what caching policies are in use in that case. Okay? The only way to deal with this really is if the server really keeps track of which clients are caching a file. Okay? And every time there's a write to a file, the client tells the server saying, I have made a change. And then the server can tell the other client saying, file has changed, please throw away the copy of because it's out of date. Okay? So only if you do this can you ensure that all data will be consistent. You will not have the problem. Okay? Now what I just said is actually what is referred to as a stateful server. The server has to keep track of where are the copies cached, who has cached a copy. Every time there's a change and a request, a notification comes from a client, you have to broadcast an update saying throw away your copy because it's out of date. Okay, all this is expensive to do. This is referred to as a cache consistency protocol, what I just mentioned. Right? Many operating systems take the shortcut. They say let's not bother. Okay? Let the user deal with it. Okay? Maybe they'll see a problem, and that's okay, they can figure it out. Okay? So if you want to actually have consistency, you will have to do the extra work. Okay? If you don't do this, you will see what the weird issues that are just piled to the server. So for up to 30 seconds, everything may be out of sync. So that's the policy. It's not necessarily a good one, but it's simple. Okay? You don't have to implement any complicated mechanism. Okay? The reason NFS implements these policies, NFS has a policy decision to keep the server stateless. The server doesn't track anything. Okay? It doesn't know who has cached the file. It's all the client job. If the server doesn't keep track of it, you cannot tell when the file has changed who should invalidate it.
Is that a two-way synchronization? So if someone, a second party changes foo.text while you are looking at foo.text, will that be updated with NFS?
NFS doesn't do anything, right? So NFS has, here if you update it, if you hit save, and you update it, after 30 seconds, these changes are, okay, so it will take up to 30 seconds for this to go. Okay. Now because the server is stateless, it doesn't even know that client 2 also has a copy of it. It's up to client 2 to actually check with the server saying, has the file changed? So every few seconds it may go and say, I have a copy of these blocks concurrent on it. If the server was stateful, the server would say, this file is actually cached by client 1 and client 2. It would actually keep a list. So when this change comes, it can send a request to client 2 saying, I have a new version. Right? So if you happen to be still accessing it, come back and get the new version. This it doesn't do. You can have file systems that do it, but NFS doesn't. So all this is referred to as cache consistency. Okay? It's important when you have a distributed file system, or actually any distributed systems for that matter that implement caching. You have to deal with consistency. Now I'll come back to this write through, as I mentioned just a few lectures ago. Anytime you have caching, you have to decide whether you write through or write back. Okay? Write through says whenever you make a change, that write propagates all the way to the remote side and hits the local disk. Okay? Write back essentially says changes are only made to the local copy and you propagate them at a later time. As you can imagine, NFS, all that we were talking about, is a write back policy. Write back policies are more efficient because we only make changes locally and at a later point to send those changes over. Okay? So you are trading performance for, in this case, for consistency properties. And you may have stale versions of your file floating around for some time until the changes are sent back. Okay? In write through, every change, every write is actually sent all the way to the server. Yeah, so changes are made immediately known to the server. It takes longer because you are no longer doing local writes. You have to do remote writes. You have to actually make an RPC request to the server, tell the server here's new data from the file. It takes longer. Okay, so it's slower, but there are better consistency properties because the server is always up to date. Server is never behind. Okay, the write back policy, the client may be ahead of the server by having more recent versions. There are two other dimensions here. The second dimension is who is responsible for ensuring consistency. Is it the server's job or is it the client's job? Okay. What I was talking about here, where the server actually, client tells the server, that is referred to as client-initiated consistency. It is the responsibility of the client to tell the server when files are changed. In server-initiated consistency, the burden of ensuring consistency is on the server. The server has to keep track of which clients have each file. Anytime a file changes, it has to tell all the clients that files are changed and so on. So in this case, the clients are dumb and the server is smart. Client-initiated consistency, clients are more complex, the server is simple. It doesn't do much. It's the client's job to deal with. So depending on whether you put the burden of consistency on the client and the server, you will get one or the other. Okay? So I think we will stop here and then we'll do the case study on NFS next time. Okay? Before you leave, for those of you